Log on, tune in, find out. Another good idea from Cambridge.
Thank you very much for the invitation to be here. It's a great program to be a part of. The talk title is Special Determinants in Higher Rank Brill-Noether Theory. So I want to start just by recalling classical Brill-Noether theory. Okay, so what's a classical case? Is we consider the question, you could think of it as the moduli of linear series on a smooth projective curve. C of genus G. And what do I mean linear series? This is a pair of a line bundle together with a space of global section. So L is a line bundle of some degree D, and V is a subspace of the space of global sections of L, which classically they denoted having dimension r plus 1. And you write GRDC is the space of such pairs. And so classically you would either study this space or you would study just the locus of line bundles which have at least r plus 1 sections. So that's the image of this space inside pick D of C. And just for convenience, it's nice to choose one of the two. So I'm going to work with this space throughout the talk. So Brill-Noether stated in the 1870s the following theorem. So let's set the number rho to be equal to r plus 1 times d minus r minus rg. Then the dimension of GRDC is always greater than or equal to rho, and GRDC is non-empty as long as rho is non-negative. And that furthermore, if the curve C is general, the dimension is actually equal to rho. Yeah?
No, the RG is G minus R plus 1 times G.
Yeah.
In the way it's usually.
Yeah, you can rewrite this differently as, yeah. Yeah. I guess I'll write this a little bit differently when I get to the higher rank case. I think it'll match what you have in mind. So this is the theorem, which again was stated in the 1870s, but the proof really took a century, and many people And this last part was the last part to be proved. it was finally proved with degeneration techniques by Griffiths and Harris. Okay, so that's the classical Brill-Noether theorem. And a natural question to ask is, what happens if we generalize by replacing the line bundle L with a higher rank vector bundle? So maybe I should say a few words of motivation for this. The classical study of linear series, of course, it's very closely related to the study of maps from curves to projective space, and that's an important topic in and of itself. But also it's related to the study of Weierstrass points. It turns out to be related to the geometry of the moduli space of curves, because you can construct divisors on it using Brill-Noether loci. So a lot of that carries over to the higher rank case as well. So I'll just say that. So this is related to maps from curves to Grassmannians. And it can also be used to construct divisors on MG. So one example of this is the paper by Farkas and Popa, where they give a counterexample to the slope conjecture. They construct this divisor with 4 different interpretations, and one of them is as a rank 2 Brill-Noether locus. So, so that's one place that it comes up. Okay, so unfortunately, when it comes to this question, even if we just ask about rank 2 vector bundles, in some sense, we're not even where we were in the 1870s yet, because we don't have a comprehensive conjecture for what should replace this theorem, right? So I mean, let me just say this. So even for rank 2, we have no comprehensive conjecture, and I would say we're not even really anywhere near one. So let me describe 2 of the things that complicate the situation. So maybe I'll break it up into sort of 2 categories. So one of them is, I'll say degeneracy, and I'll explain what I mean by that in a minute, although I want to leave it deliberately vague. And another one is special determinants. So maybe first let me go back and just point out that a consequence of this theorem, if rho is negative and C is general, then this space is empty, right? So you might ask for some comparable thing. So, well, maybe the first thing I should do is say that it's not totally hopeless, right? So there is at least a natural generalization of rho. And so this will be a generalized row. I'm going to have to switch notations. I'll say what the notation is going to be in a second. I'll write down row. Well, I'll leave this here. Okay, so this is the generalized one where now R is the rank of the vector bundles. G is still G, D is still the degree, and K is the dimension of the space of sections that we're looking at. So this is what we were calling R plus 1 before. So this number is a direct generalization of that number, and roughly speaking, this is the dimension of the moduli space of vector bundles, and this is the expected codimension you get from a determinantal construction, which, if I have time, we'll talk about later in the talk.
You've actually written that as a plus term at the end. You've written it correctly, but really you expect both things to be positive. Sorry, the second one to be negative.
So yes, that's right. So this way, again, this is something that I pay less attention to because I always work with the space of pairs, which, you know, if D is large, then it can be bigger. Yeah, so this is why I don't have the bias towards a plus or minus. But that's right. Classically, you would put a minus sign here and change everything there. Yeah. And maybe just, since you bring it up, let me give the notation, just the natural generalization of this. G, K, R, D, C is the space of such pairs. And so what can we say? Well, we do know that this always has dimension at least rho, or rho minus 1, depending on whether or not you like stacks. So the dimension of GRDC is always greater than or equal to rho, again, minus 1 if you like stacks. So, and so I should say there are many partial results. Producing components of dimension rho. So it's not somehow that this rho is just the wrong number, that we've somehow blown it. It certainly is the right number in some sense. But as I said, we have these two situations where we get things that we don't expect. So let me just explain briefly how that works. So degeneracy says, well, let's just, so for any K, D, and we'll just work in the rank 2 case for the moment, we can choose some line bundle well, say a pair of line bundles, L and M of degrees D and little d minus d for some very large d. Okay, and then you just consider the vector bundle you get by taking the direct sum. And, well, so this has many global sections. And in particular, it can be chosen to have greater than or equal to k global sections, as long as D is sufficiently large. So the space is non-empty. Yes, very unstable. Yeah. So in some sense, this is the less interesting pathology. So even if rho is very negative. Okay, so maybe let me verbally say, I think it's a good idea when you're working with vector bundles to work with moduli stacks rather than the coarse moduli spaces. When you're working with line bundles, the automorphism groups are always the same, so you don't lose very much by passing to the Picard variety. But for vector bundles, unless you're restricting to the stable locus, you get really pathological behavior as soon as the automorphism groups jump dimension, and I think you get much nicer behavior if you work with a stack. Even if you just restrict to the stable locus, you have this annoying behavior that you don't have any universal families usually without passing to an atoll cover, and then you either get very hand wavy or you have to do a lot of extra work. And somehow it's totally unnecessary. For the questions we're asking, you can ask all of these same questions in the context of stacks. And if you're familiar with stacks, you might object, well, sure, rho could be negative and this stack might be non-empty, but actually the stack of things of this form also has negative dimension. This is one of the weird things that can happen with algebraic stacks. So maybe this isn't actually violating anything. But if you actually do the math, you see that the dimension of this goes down linearly with k, and the dimension of this goes down quadratically with k, or rho goes down quadratically. So you're still violating the expected dimension. So this is a pathology, but again, we can avoid this by restricting to, say, semi-stable or stable cases. So I'm not going to say much more about this. So from my point of view, what's more interesting is the special determinant pathology. And this really goes back to two papers, one of Bertram and Feinberg and one of Mukai, that were done around the same time in the 1990s. And I'm not going to go into the details of this now. Hopefully I'll have time later. But I want to at least give the statements. So we can generalize what we've done. So we can consider fixing the determinant of our vector bundles. To be some chosen line bundle, say L, and you take D, and then we get a space which I'll denote the same as before, except I replace the degree by the line bundle L. And the expected dimension is now going to be rho minus G. Okay? So what Bertram, Feinberg, and Mukai noticed was that if you consider the special case that the vector bundles are rank 2 and L is the canonical line bundle on C, then actually you get a larger expected dimension. So in fact, the dimension of this space here is larger by a factor of, so instead of rho minus G, we get rho minus G plus K choose 2. All right, so there's this discrepancy here. And if K is large relative to G, then you actually get components that are larger than rho itself. And this is a source then of other counterexamples to expected dimension, where you restrict yourself to the locus of canonical determinant, but you get components of dimension strictly larger than rho. So yeah, let me not say more about this at the moment, but again, if I have time later, I'll come back to it. Basically, the idea is you have some kinds of hidden symmetries. Maybe I'll say a couple of words about it now, just in a very hand-wavy way, that as I suggested, all of these expected dimensions come from determinantal calculations. And well, if you ask yourself, for instance, how many conditions is it for an n by n matrix to be equal to 0, that's n squared conditions. But if you know a priori that the matrix is symmetric, it's a lot fewer conditions. And this is the sort of thing you get to get the smaller codimension and these larger dimensions. Maybe the one thing I will say is that they conjectured that this is sharp. So they made very precise conjectures about what this space should look like, and basically that it should be analogous to the classical Brill-Noether situation. And that conjecture is, there's been progress, at least some parts of it are open. So, but what I'm going to talk about now is trying to generalize this and make it into a systematic approach to come up with what might be reasonable conjectures on what a generalization of the Brill-Noether theorem should be, at least in the rank 2 case. I'll have a little bit to say about higher rank, but not very much. Okay. So let me begin just by stating some theorems, which the first couple of them are in a preprint from about a year ago. So the first one is so we fix our determinant to be L, and we consider delta is going to be the degree, the smallest possible degree of an effective divisor capital D such that H1 of L twisted down by D is non-zero. So it's at least 1. Then the dimension of the space GK, so we're going to fix rank 2 with determinant L. Again, we compare it to the expected dimension for fixed determinant, which is rho minus G, and we get that actually it's at least this plus K minus delta choose 2. Okay. So a special case of this, of course, is when L has non-trivial H1 to start with and delta is 0, and we recover a generalization of that formula. So let me just write that out separately. If H1CL is already at least 1, then we get that the dimension is the same as the result gotten by Bertram, Feinberg, and Mukai. So this is a generalization of their result. It's not that L was canonical that was so special, but just that it had non-trivial H1 is already enough to get this modified bound. So now we expect, of course, that in some sense the more special L is, the larger modified expected dimension we should get. And so we try to generalize this. And the first result in that direction is the following theorem. So now let's suppose that h1 of L is at least 2. Then we get another modified expected dimension. Like this. Okay. So somehow the argument for this theorem was a little bit harder than the original Bertram-Feinberg-Mackay work, but not much. It's a relatively straightforward generalization. This one turns out to be quite a bit harder. But the answer is still very nice. So hopefully that maybe there's a nicer approach to it. And now I want to mention a couple of results that are more preliminary that I've just been working on recently. I haven't had a chance to write them down, so I can't vouch 100% that they're correct. But let's see. So now, these were studying the case of rank 2. We're going to relax that restriction, and we're going to relax the restriction that we're only looking at h1 at least 1 or 2, but we're going to be very restrictive about k. So we're only going to look at k equals r. Or maybe first I'll do the rank 2 case. Yeah, let me do that first. Okay, so now let's suppose that h1 of L is at least m. Of course, the natural thing to do is you want to stick an m in here. And it's going to be a little bit subtle to do that in general, but at least in this special case, we can do that. So we're going to consider, we're going to let this be replaced by an arbitrary number, but we're going to restrict k drastically to look at just the minimal interesting case, which is k equals 2. And in this case, at least, we get what we want. K choose 2, it's just 2 choose 2, so that's just 1 here. Okay, so of course, there's a systematic approach behind these results. And so speculatively, if we've got that h1 is at least m, we should have that the dimension of this space sorry, we can do, say, for any rank, is at least rho minus g plus m times, and that 2 there was, the 2 in the binomial is really just the rank. So we should get something like this. So this is one of these things that looks very nice until you start to think about it. And it gets very strange very quickly. So let's observe that if either, so in some sense, why was the case m equals 1 and 2 easier than 3 or higher? Well, one reason is if you go back to the formula for rho, here you've got a minus k squared, right? That's what forces the dimension to go down as k gets larger, okay? As soon as you're adding 3 or more times k choose 2, you'll have a situation where the expected dimension is going up for large k. And that's really weird. And the same thing happens if r is at least 3, because then you're adding a cubic in k. So if either m is greater than or equal to 3 or r is greater than or equal to 3, we have actually that rho increases with k for k large. Okay, so we don't just throw this out. I think that what's going to happen, so we'll need some non-degeneracy hypotheses, basically. So in this direction, again, preliminarily, I just figured this out last night, so I really haven't had time to check it. We can generalize this previous theorem, which was the case k equals 2. We can allow r to be anything, and we do find that we get the correct generalization. So but I'll have to impose a non-degeneracy hypothesis. So then any component of space, GR, so now we let K be R is going to be the smallest interesting case here, containing non-degenerate pairs, which I'll say what I mean by that in a second, has dimension at least the same formula as before. So, well, it's exactly what's predicted by this. A k equals r, you just get the plus m. And now I have to tell you what non-degenerate means in this case. And ideally, it's something that recovers that theorem, and it does. Where a pair EV is non-degenerate if V is not contained in any subbundle of E of rank r minus 2. Sorry. Okay. So you apply this in the case rank 2, this condition is automatically satisfied, and that's why there's no non-degeneracy hypothesis in the previous theorem. But as soon as you get to rank 3 or higher, it becomes a non-trivial condition. And this is an example of why I don't want to try to pin down in advance the notion of degeneracy. You know, it's very tempting to say everything is contained inside a subbundle or something along those lines, but I think the experience from trying to generalize these arguments says it's going to be something a little subtler than that. And what I'd rather do is just try to see what hypotheses come up naturally in the proofs and see where that leads. But let me just underline that what this shows is before we were saying that degenerate cases could give you components of larger than expected dimension. But here we're having the opposite phenomena, right? I'm only proving a lower bound statement in these theorems, but I'm saying for that proof, you need a non-degeneracy hypothesis. So it appears, and I have to say it appears because I would have to prove something slightly more general before I could really say I have a counterexample, that degeneracy can lead to components of smaller than the expected dimension as well as larger. So, why is it r minus 2? I mean, yeah, no, that's a very good question. And somehow you might guess it should just be that it shouldn't be in a proper subbundle, period. So what comes up in the particular argument, I'll say maybe a few words now, and then if I have time at the end, I can try to say more. But basically what's happening is you've got a multilinear form, specifically an r-linear alternating form. And you've got some kind of kernel and a restricted map, which then gives you something. I mean, you suppose this condition fails. You get the kernel of a certain map, which you then construct as a degeneracy for the r minus first wedge product of this space. And the only way it turns out that you can get degeneracy in the r minus first wedge product is if they live in some proper subspace there. So there's sort of a two-step reduction, and that's why you end up with r minus 2. But yeah, I don't know. Okay. So one other thing I should say, though, is, of course, we'd like to be getting towards a conjecture, right? I mean, we have a sequence of lower bounds, so we'd like a conjecture. So here's one positive sign, but very mildly so, is theorem, again, preliminary, which is that this theorem here is sharp if C is general. So in the case that R equals K equals 2, the dimension is actually equal to the expected one. And in some sense, this is really a toy example. We shouldn't make too much of it. Already in the classical case, before you tried to fix determinants, this was a result of Montserrat Teixeira-Bigas. She just explicitly goes through by hand and checks that you can't get anything of larger dimension. And basically all I'm doing is going through her proof again and checking that we're okay in the fixed determinant case as well.
When you say C is general, is general modulus or general admitting line bundle with this degree and this?
Oh, yeah, that's a good question.
It might be of exceptional validity.
That's a good question, and it partly depends on how strong you want this statement to be. I think, and again, I would have to go back and check more carefully. I haven't written down this stuff yet, but I think that if you're willing to only look at stable bundles, that it's enough just to say that C is not hyperelliptic. And if you want to, but I think this might even be true even for unstable bundles. And there, maybe you need to see as Brill-Noether general for G1Ds in general, something like that. But it's not directly related to the existence of the particular L. Yeah. Okay. So, I mean, maybe, so for the case of rank 2, and I really think it makes sense to try to come up with a conjecture for rank 2 before trying to do arbitrary ranks, because you see, these complications have the feeling of an inductive structure, right? The unstable degenerate case is you contain a subbundle of large degree, and the special determinant also involves special line bundles somehow. So the feeling might be that for rank 2, things might be happening because of relations to special line bundles of one form or another. And for higher rank, you might have to worry about rank 2 bundles and so on. So it seems to make sense to start with that case. So we might hope that the correct expected dimension is determined. And again, let me just go back and remind you that even if we could prove a statement like this completely generally, this would not be sharp, because we already have in this theorem this idea of twisting down by divisors to produce H1, providing a larger expected dimension. So, so there's something missing from this whole side of the story. And so you could speculate that it would be determined by a sequence, say delta 1, delta 2, etc., where delta m is the minimal degree of a divisor, of an effective divisor d, such that if you twist down by d, you produce at least m h1. So maybe you get a sequence of expected dimensions and you take the largest one and that gives you the right answer, something like that. But at this point, I have to say, this direction of generalization seems less clear at this point. And I mean, of course, I could just make something up, but this speculation is grounded in something very reasonable, in the sense that I could state a theorem that on an open subset of this thing, the dimension is at least this, but it wouldn't be a very interesting theorem because I don't have a very clear description of what the non-degeneracy condition is, but it's a sort of a transversality condition. And so what one really wants is to translate that into some nice, clear criterion in terms of the pair itself, as in, let's see, well, for instance, like in this theorem here, we have this nice notion of non-degenerate that's very explicit in terms of the pair. Obviously, that's what we would like to have here, too. But, I mean, somehow, for some notion of non-degenerate, this is true. And I don't have a generalization to this kind of sequence yet. So that's one thing I'd really like to do. Okay. So for the last part of the talk, I think I want to shift gears a bit and talk about how you might prove something other than lower bounds on dimensions. And so that's via degeneration arguments. So, as I said, the original Brill-Noether theorem was proved via degeneration. And at this point, it's pretty easy to give a very short proof of that theorem, both the non-emptiness and the expected dimension parts using degenerations. And so one would like to do something similar in the higher rank case. So really the main person who's been working on this is Montserrat Teixidori-Vigas. And so she has generalized the theory developed by Eisenbud and Harris of limit linear series. To the case of higher rank vector bundles. And she's used it to prove various existence results, maybe some non-existence results as well. Maybe I'll focus on, so prove various results on existence of components of expected dimension. And I'll say that there is this conjecture I mentioned of Bertram, Feinberg, and Mukai, and to approach that conjecture, we want to be able to do the same sort of degeneration arguments in the context of fixed determinants, and in particular in the case of canonical determinant, but more generally in the case of special determinants. So to approach the Bertram, Feinberg, Mukai conjecture, at least the non-emptiness part of the conjecture, which is the main part that's still open at this point, we want to adapt this machinery to special determinants. And so let me briefly sketch what the issue is. So limit linear series theory relies on dimension counting. And the issue is that in order to prove anything using limit linear series theory, you need to show that you have the expected dimension on the special fiber. And Bertram, Feinberg, Mukai are saying precisely that you don't have the expected dimension, that it's larger by k choose 2. So you need to show that the symmetries that they discovered for the case of canonical determinant can also be found inside the limit linear series machinery. So, and this is actually highly non-obvious. So it's not obvious how to extend the symmetries found by Bertram, Feinberg, and Mukai to the limit linear series context. Okay, and so this is what Teixidor and I have been working on lately. And so here's a theorem at least. Which is that it's okay in the case of degenerating to curves with two components. So limit linear series arguments work in the canonical determinant case for degenerating to curves with two components glued at a single node. And so this is the simplest sort of degeneration you can do. And actually, in the classical limit linear series theory, that was often enough because somehow the theory was described in an inductive manner, and usually you could degenerate as far as you wanted by inductively breaking off one component at a time. The problem is for higher rank vector bundles, it's intrinsically non-inductive. You've got to worry about the gluing maps at the nodes as well as stability issues. So, so this isn't enough, but I should say that it appears that the same arguments will generalize will work for degenerating to any chain of curves. And this appears to be the key degeneration that we want.
I'm not understand the contents of the theorem because you said that was the unit very big.
So, yeah, so the idea is you define this notion of limit linear series. And what you want to say is that if you take a degeneration, you've got a family of smooth curves degenerating to something like this, and if you can prove that the limit linear series, say with fixed canonical determinant on this curve, are non-empty of the expected dimension, then you conclude that at least this has a component which is non-empty of the expected dimension. But the problem is that this has to work now for the modified expected dimension in the Bertram-Feinberg-Mukai results. And that's where the difficulties come in. So somehow if you just generalize Eisenbud-Harris, it works fine for the varying determinant case where there's no special symmetries. But then you want to simultaneously incorporate the dimension counting for the limit linear series with the symmetries of the dimension count in the canonical determinant case. That's what turns out to be more difficult. And so that's what we're trying to do here. And that's what the theorem says we can do for this case. And I think more generally, any sort of chain of curves is going to be okay. And maybe I'll say just a few words about the situation is that the Eisenbud-Harris definition of a limit linear series involves having a linear series on each component with some sorts of ramification conditions at the nodes. And if you had canonical determinant on this one, then the determinants of the bundles that you look at on these components are pretty far from canonical. And so that's where the symmetry gets screwed up, and it's very hard to recover it. And so in fact, I don't know how to give a direct proof if you just use the Eisenbud-Harris definition. But in my thesis, I gave an alternative construction of limit linear series where basically, instead of just taking these extremal degree line bundle on this component and this component, you remember all the intermediate degree ones. And there you have a better approach to keeping the symmetry in the construction. And so we're able, basically, the construction in my thesis relies on introducing a notion of a linked Grassmannian that generalizes the Grassmannian. So you replace the Grassmannian in the determinantal construction with a linked Grassmannian, and everything goes through. And now what you want to do is introduce a notion of a symplectic linked Grassmannian to sort of see what's going on with these symmetries. And that's what we do in this paper. And so ultimately, the hope is that we can prove the existence part of the Bertram-Feinberg-Mukai conjecture using this result, and that this will be the main technical machinery that will be necessary to do it. And one hopes that once you have this, you can look at these curves and prove that you have the expected dimension and get the non-emptiness statement there. So that's the basic, the gist of what we're doing with that. Yeah. I should have asked at the beginning of the talk, are we shooting for an hour or 50 minutes? Okay. So let me just try to give a little bit of the flavor of, I've said almost nothing about proofs of any of these things, where these things come from. by going back to the very original Brill-Noether statement and saying, well, where do these original lower bounds come from? So, so these are maybe constructions. Okay, so let's start with, let's say, M R DC, which is going to be the moduli space of vector bundles. Of rank R and degree D on C. And now what you want to do somehow is you want to take a relative Grassmannian over this of subspaces of global sections of these vector bundles, but you can't just take the relative Grassmannian because of course, the universal bundle on this, if you take its push forward, you get something that doesn't commute with phase change, and it's sort of a mess. So you use this trick of twisting up by a very ample divisor. So choose the sufficiently ample divisor on C. And let's let U be the universal bundle on the product of the moduli space with the curve. Then let G be, well, I'll just say what it is. It's the relative Grassmannian of G, K, and what we're going to do is we twist U up by D and then push it forward down to M. So P1 lower star of U twisted up by D. So this is a relative Grassmannian. It's nicely behaved if D is very ample and very, not in a non-technical sense. So then this is smooth over this. And we can construct G, the space of pairs that we're interested in, G, K, R, D, as a closed subscheme of G. And we'll do that as a vanishing locus of the induced map. So let me write it out first and then say where it's coming from. F injects into this push forward, and then that in turn surjects onto the push forward of UD restricted to D. So this induced map, where F is the universal bundle on G, okay, so that's the statement. Why is it true? Well, what does this G space parameterize? It parameterizes a choice of a vector bundle together with a space of sections of that vector bundle twisted up by D. We were interested in pairs of the vector bundle together with the space of sections of the vector bundle itself. And so this is that subspace, and it came from U itself exactly if it's in the kernel of the restriction back to D. Okay, so this is sort of following a general nonsense argument. And so this is where rho comes from. So I'm out of time, but let me just say maybe that, so for the special determinants, you modify the construction very slightly. And then what we get is a symplectic form, or some generalization thereof, on the ambient bundle. So the bundle that takes the role of this. And then you can replace the universal relative Grassmannian with the symplectic Grassmannian. And that's what accounts for the modified codimensions. So these theorems on modified expected dimensions come from trying to generalize this idea. What if the form isn't actually symplectic, but it has some degeneracy? What if you actually have a family of symplectic forms, and then you look at the intersection of the related symplectic Grassmannians? When can you say that those intersect transversely? Or the higher rank case, what you get is an alternating multilinear form rather than bilinear. And those are the sorts of things that come up. So it all ends up being sort of linear algebra and multilinear algebra in the end to try to figure out exactly what the right statements should be. And I'll stop there. Thanks for your attention.
Any questions?
What is known on this diagram from the unitary conjecture?
I guess that's a contentious question, but so you can break it up into several statements, right? One of them is that, of course, they themselves prove that on an arbitrary curve, every component has at least that dimension, but not the non-emptiness. So that's certainly one part of the conjecture. And then you would also want to prove that on a general curve, it's actually smooth of the expected dimension. And Teixidori-Biggis has a paper using a Petri map type argument to try to prove that second part. I haven't read through it carefully, but it's published. So, yeah. But the non-emptiness is definitely open. There are partial results in that direction. And in fact, I think the only published partial results in that direction are due to her. But again, they rely on filling in this background machinery. So they do the appropriate dimension counts, but missing this machinery. So part of it is to fill in those arguments. But even with that, it's not the sharpest results. You're off by some factor. So at this point, I think that's a very interesting question. I mean, I have a grad student looking at that right now, because the theoretical machinery says that, that there have to be limit linear series on these curves that we don't know about yet. But we know they exist, so I think it's worth trying to find them and see if we can prove the existence as well.
Yeah, there are actually some other results totally unpublished.
The park, yeah, exactly. So there's another approach to proving non-emptiness which tries to generalize the classical approach of calculating the class in the Jacobian. But those again are partial results as well.
They're partial results. But I mean, I think it is conceivable that they could be. They sometimes give better results than
yeah.
Not always.
Yeah. But again, Montserrat's clearly aren't sharp either for the approach.
No, neither is sharp, but I think if you could really calculate these cohomology classes,
right.
I mean, one of the problems, there are two problems. One is the non-compactness of the stable
right.
space, and the other is that you have these, you can get expressions for the cohomology class. But, and in principle, you know the relations in the cohomology, but actually to compute, to see whether the class is zero or not, so it's another question.
Yeah.
And so that's, the argument fails, the argument fails to be complete, largely, I think, because of that second reason.
I see. Yeah. So somehow, maybe just
she simplified it and just took in the end, took her class and intersected it with something or other,
right.
and got non-zero
right.
in that case. But obviously, there's a possibility that when she does this thing, it gives you 0, but something else gives you non-zero.
So, but I guess what I should say is there are cases where degeneration arguments, we think they're just not going to work. And for instance, I think Farkas and Popa tried to prove this result using degenerations to a comb curve, where you've got the genus 0 and then a bunch of genus 1 tails. And they decided that it simply gave, that those curves weren't general from this point of view. It does appear that these curves are general from this point of view, as far as we can tell. So I think in principle, this approach will work. It's just a question of really thinking what we must have been missing, or what we've been unable to find from the original papers.
I think this, what you're talking about here, should reduce at least finding out what the number ought to be to a problem in linear algebra.
Exactly. Well, again, modulo this point that you have to...
linear algebra are difficult.
Yes. But modulo this issue that we still need to understand this thing about twisting down to produce higher H1s. And I think that's certainly also an issue. And that, it's not quite as clear how to fit it into that framework yet. I'm optimistic that in the end it will, but somehow the generalizations aren't quite as obvious.
It might always appear that this, you're saying this twisting down because sometimes that could give a different number.
Absolutely.
A bigger number.
Yeah.
Then, I mean, that could come into the linear algebra in terms of things not being transverse to one another.
Yes, absolutely. Where it also comes up, I mean, so what happens in the theorem that I did state is there's no intersections, but it's simply not a symplectic form. It's an alternating form with a particular degeneracy, and you need to deal with that degeneracy. So that's a very natural place for it to come up.
Yeah.
But again, combining the two seems a little slippery so far. I haven't.
Any more questions?
For the classical Brill-Noether theory, that is rank 1, there is this strategy on the frame. Of course, that does not work. That proves the result for curves on Petri surfaces.
Yeah.
But of course, precisely for curves on Petri surfaces, the higher rank
Yes.
does not work well. But no one tried a kind of similar strategy looking at curves on Petri surfaces.
Not that I'm aware of. I mean, there are these papers that study the case of curves on K3 surfaces in great detail, but I don't know if people have tried to find curves on other surfaces that might be general or something like that. It's also, Peter Starnak suggested you might try looking at modular curves, and that would be another completely different approach, which would be, again, really cool. But
Any more questions? Okay, so can we thank the speaker again?